So thank you very much for having me. I'm really looking forward to meeting all of you and having some really interesting conversation. So I am Jessica, and I'm working in Toronto with Brian and Susan. And so I will be talking a little bit about using radio polarization and 21 centimeter H1 observations to try to learn something about the magnetic field and the warm ionized medium and the cold to neutral medium and try to combine them together to learn something about how the magnetic field may be connecting between these two very different phases of the interstellar medium. So to start, radio polarization. If we look at the galaxy in radio synchrotron polarization, we see some really beautiful structure. Of course, we see H2 regions, we see supernova remnants, and distant polarized sources. However, if we look at the Stokes maps on the right, just the polarized Stokes Q and U maps, we also see some really intricate structure. However, it's not really clear how to interpret this data. The reason for this is that we say that these quantities are not invariant under rotations and translations in the QU plane, which means that it's really difficult to try to interpret physically what these data sets are telling us. So,
Tell us exactly what we're looking at in that picture.
yeah, so that was just radio synchrotron polarization at 1.4 gigahertz from the SGPS.
Okay.
And then, so on the top right-hand corner, so that's the total intensity, and then the two on the right are the Stokes Q and U maps, and then on the bottom left, that's the polarized intensity. So just to talk a little bit about why it's really difficult to interpret these data sets. So if we imagine we're looking at some distant pulsar that has an intrinsic polarization, and we observe it in our image plane, then if we can measure its polarization, we'll measure the polarized intensity and its corresponding polarization angle, which is defined below. All super simple. However, if we happen to have some intervening foreground medium that's causing Faraday rotation, that's going to rotate the polarization and change the polarization angle that we observe. Just to kind of show you that your environment is really going to be able to affect your polarization angle. And similarly, even your instrument can be somewhat of a problem. So, for example, if you're using radio interferometers, you lose this low spatial frequency information, and so you can also lose some of the polarized intensity, and so that parameter can also change. So this is just to say that looking at the Stokes Q and U maps, a lot of environmental features and even your instrumental features can affect these data sets and make them really difficult to interpret. However, if we look at polarization gradients as we are looking at here, the really nice thing about polarization gradients is that they are rotationally and translationally invariant in the QU plane. So here's an example of the Nature paper that was published in 2011, which talked about the polarization gradient. Since then, everyone seems to be really excited about gradients, which is great. So I just have the definition below. And so the nice thing about using polarization gradients is that they can, oh, right. So I just wanted to mention that, so this is the equation that you typically see, or I've been seeing really frequently in papers. And then Chris Heron published a paper which did a lot of mathematical derivations for invariant quantities that you can make using polarization data sets. And so he just pointed out that if you want to really maximize the polarization gradient, you can just throw in some extra terms. So when you see this value, this is the polarization gradient. But also remember that if you wanted to find the maximum value, this is the equation that you want to use. So you can go to Chris Heron's paper. So the nice thing about these polarization gradients is that they can really tell you a lot about the properties of the warm ionized medium, the magnetic field properties, and the turbulence. So here again, we're looking at the same figure as the previous slide, and so you see a lot of this really beautiful structure in the polarization gradient. And how this is being interpreted is you have abrupt changes along the line of sight of either your parallel magnetic field or the thermal electron density that's causing the Faraday rotation. So these properties can be changing along the line of sight, and that's going to cause your polarization gradients. Right. So there's a small inset on the bottom corner. So this is just a zoomed in part of the entire map. And it's just to show you the detail of the structure and the polarization gradient. Pardon? So I actually don't know offhand what the exact scale is and which part it's zooming in, but
330 plus forward.
thank you. Yeah, no, yeah, you're right. You can see it here. So I guess, yeah, so if you want to start matching structure, I guess that would be this here. Right? Yeah, thank you. Yeah, so that was also I was going to point out. So those are just pseudo vectors to show you the direction along which the polarization gradient is a maximum. So you can also start doing some really fun things with the polarization gradient. Again, going back to Chris Heron's paper, where he published a variety of different mathematical properties that you can use to quantify these rotationally and translationally invariant properties of the polarization. So one thing that you can do with the polarization gradient is once you've derived this value, you can then start to decompose it into two orthogonal components. So if you think about, if you remember, if you have maybe going back, so if you think about your polarization in the QU plane, we can decompose it into components that are parallel to your polarization intensity, the actual vector itself, parallel to this vector. I will refer to that as being the radial component. And then also the tangential component, which will be tangential to that vector. So those are the two vectors that I will be talking about. I know it's a little hard to think about in your head, but I also have a depiction up in the top right corner. So again, the red is the radial component. It's parallel to that vector. The tangential is the blue vector, which is tangential to the polarized intensity vector. Okay. And so the nice thing about being able to decompose the polarized polarization gradient into these two components is that, again, they allow you to really have more of a physical intuition of what your polarization gradient is telling you. So for example, if we look at the radial component of the gradient, you can imagine that you can have situations where your intrinsic polarized intensity is changing, or you can also have depolarization, which is causing that strength of the vector to be changing. In contrast, the tangential component would be changing the polarized angle. So you can imagine that that would be caused by things like Faraday rotation. And so being able to decompose the gradient into these two components really allows you to get some kind of physical intuition of what is happening in the warm ionized medium. Taking a somewhat different direction now, looking at a very different phase of the interstellar medium. So the atomic ISM has one of the phases being the cold to neutral medium. And so Susan has done a lot of work on this phase of the ISM. So here we have a map of H1, atomic H1 from Galpha H1. And we see a lot, again, we see a lot of this really beautiful linear structure here. And the way that you can start to see the CNM structure is looking at really thin velocity slices. And so if you limit yourself to narrow channels and velocity of this atomic H1, you can start to probe this CNM structure. And what she found and what she's been doing a lot of work on is that these CNM structures, these linear fibers, seem to be correlated with the magnetic field. And so even just looking at the CNM, we can also learn about the magnetic field in this very different phase of the ISM. So up on the top, using H1 data, specifically the CNM phase of the H1, she's been able to show that you can actually predict what the magnetic field should look like just solely based off of the morphology and structure of these fibers in CNM. So that's the top in blue. The white are pseudovectors overlaid for the starlight polarization. And just for comparison below, it's playing the same game but with Planck dust polarization. So this is just to show you that even in the CNM phase where there's very low ionization fraction, you can also learn a lot about the magnetic field in this very different phase of the interstellar medium. And so what I'm interested in is we have information on the magnetic field in these two different phases of the ISM. The question now is, can we somehow relate these two? Does the magnetic field actually know about these two phases of the ISM, and are they connected with the magnetic field?
Now, these WIM and CNM are mnemonics,
So there's
which
the
we take seriously, but do we know whether they're really distinct phases?
whether the worm ionized medium itself is a distinct phase, and similarly with the CNM.
Well, I'm saying, do we really know it?
Can you please use your seat mic?
Sorry, I think they're asking you to use the button.
I know. Maybe we should say that.
Okay. Okay. Right. So I suppose moving forward then. So one way that, so this is very preliminary, but one way that I've been looking into whether or not these phases actually know about each other is trying to look for some spatial correspondence between the polarized gradient of synchrotron radiation, which is probing the warm ionized medium, and the H1 linear features that's probing the cold neutral medium. And so since we believe that these structures are really probing magnetic field properties, I'm now looking for correspondence between these two to try and use the magnetic field properties to relate the CNM and the WNM. The WIM, sorry. So here what I've done is I didn't have time to talk too much about the rolling Huff transform, but this is a coding software that Susan wrote. And all you really need to know is that what the rolling Huff transform does is it finds linear structures and maps. And so what I've done is using the rolling Huff transform in these two, in the polarization gradient and the H1 structure. And what I've done is then compared the angle of orientation basically for these two different maps, just to see if they have any spatial correspondence between the two. But you can see in the top one, so for the RHT angle, you can see that there's these two very strong spikes close to the horizontal. So these two strong spikes here, I believe that these are from basket weaving features that come from the telescope scanning that took the data sets. So what I started to do was I just started to, obviously I don't want to be correlating those features because those features are very linear, so of course the RHT is going to pick them up. So what I've been doing is I've just been trying to use spatial filters to try to filter out different basically spatial resolutions. And so the H1 has a native resolution of 3.5 arc minutes, as does the polarization gradient. But I want to really reduce those basket weaving features, so I've just been kind of playing the game of lowering the spatial resolution to try to minimize those structures, and then just continuing to do that and look at the distribution of spatial angles. And then somewhat similarly, again, because I only have a minute now, I did something very similar with what's called the histogram of oriented gradients written by Juan Soler. And so very similarly, using first the rolling Huff transform to pick up the linear features in these two different maps, where in the top, the red is the H1 linear features and the blue is the linear features in the polarization gradient. I then use the histogram of oriented gradients to try to compare these structures. And then so the bottom shows two different resolutions from these plots. So I picked out two different resolutions and tried to compare their relative orientations to try to look for similarities. So again, this is just very preliminary, but this is kind of what I've been doing. So thank you very much. Do I ask? Do I pick? Okay, yeah.
So you had the velocity information with H1. Have you been looking at the total integrated intensity, or have you been binning by
Yes,
DPN
that's
to see if that makes any difference?
yeah. So that's a really good question. So just to start, I've been picking out certain velocities, and so I made sure to point out that this is preliminary because I'm fairly certain that I've for now chosen velocities that don't actually correspond to the CNM, that they might actually more likely correspond to the warm neutral medium, which you'd be more likely to be correspondent. But yes, so I've just started out by picking certain velocities, and then I'm going to be stepping through them and then integrating. I'm just trying out a whole bunch of things. Yeah.
There's two dimensionless
Oh, I think they
numbers.
need you to push the button.
There's two dimensionless numbers that would be of interest physically. One is the ratio of the magnetic pressure to the thermal pressure, and the other is the ratio of the magnetic pressure to the rho v squared, the turbulent velocity. Do you have any measurements for either one of these?
I have not done that, no.
Has anybody done it?
I don't know.
So in one of the papers with Brian, we did estimate those numbers, the alpha and Mach number and the plasma beta from the polarization gradients
Right,
as compared to simulation. So they're transalphinic and subsonic. So it's
Okay.
the H1 though is a huge range probably.
Yeah, but I'm just curious what the characteristic numbers are. So
One Siemens splitting data show that pretty well. The magnetic pressure is a few times the thermal pressure, typically.
so the magnetic pressure is a few times the thermal pressure
Yeah,
and comparable to the
to the
rho v
Turbulent,
squared. Yeah.
that's the usual.
Okay. I mean, that was my guess, but I wondered what the observation said.
Okay.
In my talk, I will be. Oh, I'm sorry.
Yeah.
In
The
my
button.
talk, I will be discussing the gradients both of velocities.
Yes,
and,
I'm looking forward to
yeah.
your talk. Yes. Yes.
So, and I think many questions could be then discussed.
Yes, I think we should definitely talk about this. Yep.
Looks at your picture, the structure from H1 and the polarization gradients looks different.
They do.
But why do the histogram look similar?
Right, because they don't. So the histogram of oriented gradients, it doesn't take. It's not a pixel by pixel basis. So you could imagine that if you had a lot of structures that were. So if you imagine these two phases were in fact, their structures were dominated by magnetic fields, and you imagine just like very simplistic that you have linear structures that are all along the magnetic field, but they're displaced, right? So they wouldn't necessarily be spatially coincident, but you could still get very similar distribution of angles, even though they're not actually spatially coincident, that they could be offset. So this would take into account that some things might be offset. But that's also why I've just been doing a variety of things. So.
I'm supposed to check if there are any questions from
Oh,
the
right.
cloud.
Right.
Nope.
There are no questions at this
Okay,
time.
Perfect. All right. Thank you very much. Are you next? Okay, good. All right. Our next speaker is Giles Novak, talking to us about observations of the polarization spectrum of dust emission. Whenever you're ready.
So is my mic working? Is it on? Thank you. I guess we're waiting for this picture to come back. Here it is. Good. Thanks. Okay. So as was mentioned by Susan who introduced me, I'm going to be talking about the polarization spectrum of dust emission. And I'm going to start with two detailed whole cloud magnetic field maps that are familiar by now. And these cover spatial scales, as you can see, of tens of parsecs. And yet they have angular resolution below a parsec. The one on the right was made by Planck. Planck mapped the whole sky in this way, but only for the closest few clouds, maybe 3 or 4 clouds, were they able to get this very detailed sub-parsec resolution. On the left, you see an image from the balloon-borne experiment BLAST. And we obtained better angular resolution with this experiment. So we're able to make this kind of sub-parsec map out to greater distances. Vela C is about 7 times further than Taurus. And this is an ongoing experiment. We hope with a flight that we have planned for later this year, we'll have many dozens of these kinds of maps. But one of the drawbacks of interpreting these maps is that to a large extent, we don't really know when we make a map like this if we're mapping the field, sampling the field direction through the whole cloud or just on the front and back surfaces. And this is due to uncertainties in the grain alignment mechanism. So I'm going to list, briefly go over some of the ways that observers are trying to constrain this problem so we can make better use of these maps. One of the key ways is to look not at the angle of polarization you see here, but the degree of polarization to see how that correlates with column density. We can also look at the same effect in the near infrared, polarization by absorption. And in this case, we have some nice techniques to use the polarization spectra to further constrain this loss of grain alignment deep in clouds. And then finally, Laura Fissel, who's actually here at the meeting, has done some very nice work, again, using the emission technique, but showing that when you bring in a third variable, you can get even, and when you also compare with simulations, you can get even more information on loss of grain alignment. The third variable is the local dispersion. But I'm going to talk about what polarization spectrum might have to add to this. So some very basics on the polarization spectrum of dust emission. If you have a very simple model where all your grains are exactly identical, then it was shown quite some time ago that the polarization spectrum doesn't have much information. It's very flat. So what you need if you want to get interesting polarization spectra is multiple grain populations. For instance, you got multiple sizes, multiple different compositions of grains. So in this simple cartoon here, I show a one grain population. These are observed all together, all in your beam, so you don't separate them, but the cartoon shows how you have two populations in this simple model, one emitting at shorter wavelengths, having a higher polarization, one emitting at longer wavelengths, having lower polarization. So you see you get a falling polarization spectrum. So with these different components, you can get rising. You get interesting shapes if you have multiple components. What you need is you need to have correlations between the parameters that govern the emission of the different components and the alignment. And you can do that not only with different types, even if all the grains are identical, you could have a different radiative environments. You could look through a cloud, you could look at the surface, you could look at the deep in the cloud, and you could have different, you could have correlations of the type I described in that way. Okay, so what do we see when we look at observations? Well, there's only two cases where we actually have whole cloud polarization spectra, and these were done by the BLAST, 2 papers by the BLAST team. What we've done here is we've combined these are from our last flight, and we've combined, and the spectra here is shown in colors, we've added a point from Planck. We have 3 colors from BLAST, and we add a point from Planck. We get almost a factor of 4 in, about a factor of 3.5 in frequency coverage. And also, I'm showing a model. It's actually the only model that's ever been done for polarization spectrum of a dense molecular cloud. And it turns out that they're in agreement. The error bars here are statistical. The systematic errors are about 10%. All we can conclude from these 2 papers is that the polarization spectrum is flat to about within 10 or 15% in agreement with the model. So there's no tension. I should point out that we've normalized everything to 350 microns in this plot. And in the rest of the talk, I'm going to tell you about what SOFIA can do. So now we're pushing with the airborne telescope into this frequency range here, the far infrared. But before I tell you about that, I want to mention there's actually 3. There's not 2, there's 3, but the third one's very different. The third BLAST result is actually the first measurement of the submillimeter polarization spectrum for a translucent molecular cloud. It's also flat, but that really should not necessarily even be on this plot because should not be compared to this dense molecular cloud model. It's really more, we compare it with models developed for the purposes of understanding cosmology foregrounds, and it's of interest primarily for that purpose, but we are able to show that some of the models that have been published are disfavored by this observation. Okay, so now I'm going to move on to the target of Sophia. So what we looked at is, what you're looking at here is a column density map of L1688, which is a portion of the Ophiuchus molecular cloud. And it has, this part of Ophiuchus has very high column densities, at the peak up to 100 magnitudes. And what we studied with Sophia is this one core here called rho of A, where the actual column density reaches the highest value found in this cloud. We observed it at two different wavelengths in the far infrared, 89 microns and 155 microns. And this is a paper that's hopefully going to be submitted very soon by Fabio Santos, led by Fabio Santos. So one of the interesting, important things about this cloud is that its heat source is primarily a target. I should have mentioned these stars are all protostars, but there's another target that's not given a star symbol because it's not a protostar, but it's a young B star, a very bright star sitting right about here in this hole in the column density. And it's the main heat source for rho of A. And you can see in the next slide here what it's doing to rho of A. So this shows these contours. There's a blow up showing these same column density contours that you saw here. And now you see this B star of S1. And the color here shows the temperature. So the core, where the radiation from the star doesn't reach, we go below 20 Kelvin. But on the eastern side of the cloud facing the star, it gets above 50. It's about to 50 Kelvin approximately. So our polarization data that we got, it's a very detailed map. We have thousands of individual measurements at both wavelengths, and we cover way out into this eastern diffuse region where the column density is lower, and into the core, not across the whole core, but through a good section here of the core of rho of A. And what I'm going to show you is not the magnetic field map, because what I'm interested in here is the ratio of the polarization measured at the longer wavelength divided by the polarization ratio measured at the shorter wavelength. And in particular, it has a correlation with column density. So this plot shows this ratio that I just described as a function of the column density going from the eastern diffuse region, low column density, to the dense core. And so what we're doing here is we're probing the slope of the polarization spectrum. The ones I showed you until now were flat. And what we're finding here is that we see positive or zero slopes for the eastern diffuse region. As we go into the core, the slope becomes negative. Now, all the models for polarization spectrum, including the two I listed before and another one just published last year, have positive slopes in the far infrared. So how do we explain the negative slope we see in the dense regions? Well, we think that to get this negative slope, you need two ingredients. You need a lot of extinction. You also need a lot of irradiation from some bright source. None of the models have both of those ingredients, but we think that for these sight lines, there's enough density, so we know we're going through a very dense core. You can't get through the core with your sight line without going through the surface. So it's reasonable that we're also going through some of these highly irradiated cloud surfaces along some of these sight lines. So that's what you need to get this structure in the polarization spectrum. You need two components, and you need these correlations between the parameters that govern the emission and the alignment of these different components. And if you think about these two particular components and what you would expect from the RATS theory, you do come up with a expectation that you'll get the negative slopes. But we wanted to put some numbers in to see whether you would expect the magnitude of effect that we see here. And so we developed a very sort of a crude sanity check type model to see whether it's at all plausible that this factor of 2 change in this ratio could be accomplished by this effect of having these two components I just described. So I'm going to briefly go over some of the aspects of this model. So it has just two components. We have a uniform cloud, and then superposed on that, we have a spherically symmetric core. Now, of course, you saw the map. You know it's not spherically symmetric, but it's a sanity check, simple model to see whether it's plausible that this could be right. So we wanted to do the sanity check, so we push ahead with this model. The core is heated from all sides uniformly. So it's hot on the outside, cool on the inside. Of course, you saw the cloud is not heated from all sides. It's only heated from the east side, but we only observed the east side, so that's probably not the worst approximation. And then finally, the key ingredient we need to get any kind of correlation is we have to have the grain alignment get turned off. So we have a certain radius within the core interior to which there's no grain alignment. And that's called the transition radius here. So just briefly, all these parameters here, which just tell you how big the core is, what the background and what the core look like, they're all constrained by very detailed Herschel observations that we have, that have been made and are readily available for this core. We azimuthally average them, and it's not hard to constrain all these parameters. This last one, of course, needs polarization data. We don't use our ratios to constrain it, of course. We use the actual polarization versus column density measurements that we have to constrain this best value of 0.6 of the size of the core interior to which there's no grain alignment. We don't include any complications of magnetic geometry, assume a uniform magnetic field for this very simple sanity check model. So this is, again, our data. I already showed you the slide showing the change in this ratio with column density. So now I'm going to superpose the results of the model parameters that I just showed you in the previous slide. Look only at the solid green curve for now. So there's no free parameters to adjust here. What you see is what you get. That's not completely true. We allow the freedom to shift this up and down because the polarization ratio where all the grains are aligned depends on grain model details. So we just let this green curve shift up and down to fit these points. So how well does this solid line fit the data? Well, there's obviously some discrepancies. The data is concave up. The model is overall concave down. Also, another thing that is, I guess, could be viewed as disappointing is if we change the transition radius to see when the model starts to not fit the data, we have to change it a lot before we get serious or even modest discrepancies. But we didn't really build the model for that to constrain anything. We built it as a sanity check, and as a sanity check, it does show that factor of 2 variations seem actually not just plausible, but maybe even from the point of view of the simple model, about what you would expect. So we're encouraged from this to push ahead with this as a way to probe loss of grain alignment. One of the next steps is to build a better model, of course. There's also older data from the Kuiper Airborne Observatory. I showed that paper by Hildebrand et al. 20 years ago. And although back with the Kuiper Airborne Observatory, none of these positive slopes were ever observed. We saw the first positive slope ever seen in the far infrared for polarization spectra. But several clouds showed negative slopes comparable to these. We could go back and look at those data to see how they fit with this picture. Also, more interestingly, there's a lot of GTO data we have in the instrument team for the Hawk Plus polar emitter, and also the prospects of getting more data. So I think that this idea of using polarization spectrum as a way to probe loss of grain alignment provides a very new way to look at loss of grain alignment, where we're looking at spectral rather than spatial variations in the polarization degree. So I think I'll just leave. I don't think I need to summarize my talk. Pretty much out of time, so yeah. CL?
We consider I did so right. Okay, so if we consider the adiabatic contraction of the core due to gravitational collapse, and it means that there are turbulence generated by converting the gravitational energy to turbulent energy. And how do you think that would maybe modify the model?
Well, yeah, as I mentioned, we just assume a uniform field for this very simple sort of sanity check model. But you're right that any careful analysis of this problem that aims at putting serious constraints on how grain alignment gets lost as you go into a cloud would need to take into account field geometry. For instance, people who have studied how the polarization degree depends on column density, if they assume that all the drop-off is due to grain alignment, they may be wrong, because it could be that there's more turbulence in the cloud also is causing some of the loss of alignment. So in the big picture, this is a very complicated problem and will require almost all the methods, or all the methods that I listed on the first slide. Laura has published a couple of papers on ways to discriminate between a field disorder and loss of grain alignment. Right? So one way is to go to higher angular resolution, but there's other techniques involving comparison with simulations. So all the techniques will be required. The technique I'm talking about is particularly good at looking at separating the warmer from the colder dust. But I don't think it has any particular advantage in telling the difference between field tangling and grain alignment loss. So it's going to require more effects. I think Alex was next.
First of all, I would like to agree with you.
Can you use your seat mic, please?
I agree with you in terms of the carbonaceous grains in molecular clouds. I would like to stress. In a recent paper, Thiem, Huang, and me, we discuss a possibility that in diffuse media, the carbonaceous grains may not be aligned, but in molecular clouds, it's very difficult, from what I know, to avoid coagulation of carbonaceous grades in the aggregates when they will have to be aligned. This is first thing. And the second thing is there is a new possibility of testing grain alignment. And there will be my talk and my students' talk the next tomorrow, discussing a possibility of using gradients and comparing gradients, which can be pinpointed to the denser regions where particular species are present, spatial molecular species, and seeing whether we see difference in polarization. We can see a possibility of determining whether grains are aligned there.
Okay, thanks, Alex. I think it was Dick and then Mark.
You have more than a factor of 2 change in the dust temperature. The ratio of the dust to the gas temperature can affect the polarization. Have you looked at the gas temperature from molecular data to see if there's any change in that ratio from one place to another?
We have not looked at that.
Okay.
Yeah, in fact, the dust temperatures we have should also be taken with a grain of salt, because they're based on azimuthal averages of the Herschel data. With a non-spherical model, we could probably do better at estimating actual dust temperatures as opposed to line of sight superposition, which are measured and published by Herschel. But that's an interesting point. Thanks. Mark.
Okay, so let me ask this question in an extreme form. Do your results mean that I should stop paying attention to Chandrasekhar Fermi ever? And the reason is because I ask that is in Chandrasekhar Fermi method, you need to say something, you need to assume something about the density of the gas in order to derive magnetic field strengths, etc. And what you're showing, at least in this one cloud, is that a lot of the signal seems to be coming from just a surface layer where the density is not anywhere near the central density, presumably. None of the Chandrasekhar Fermi papers I remember take that effect into account, and it's not clear to me how they could unless you had some more general understanding of where the alignment loss occurs. So does this result mean that Chandrasekhar Fermi should be thrown out the door?
So let me answer the first question first. Certainly, when Chandrasekhar Fermi put the method forward, they were applying it to a different object than a molecular cloud. And indeed, there is a concern that because of loss of grain alignment, this might be a problem. You could also ask about other methods like the HRO method. Now, it depends on the circumstance. Like for the case of the Planck data, Juan Soler argues that there the resolution is in general poor enough that maybe we're not getting into the range where you lose grain alignment. But I think in general, it's a big concern I have about all the published Chandrasekhar Fermi estimates is that I'm probably forgetting some more careful work, but certainly most of them do not take this problem into account at all.
It's possible to do.
Okay, so Chandrasekhar Fermi can be revived, but I should ignore all the current measurements in the literature. Good to know. If I have fewer papers I need to read,
All right,
excellent.
Or take them as approximate anyway.
All right.
Yeah.
we can talk more in the discussion. Let's thank our speaker again. And next up, we have James Cho telling us about the disruption of zonal flows by magnetic fields on a rotating sphere.
Can you hear me okay? All right. All right. So we're going to change scales now and talk about effects of magnetic field on much smaller objects like planets and possibly stars. So this is not a simulation. I'm motivated by pictures like this. This is an image from a DMSP, that's Defense Meteorological Satellite Program's satellite, which orbits the Earth at about 800 kilometer altitude, and it's looking down onto the top of the ionosphere around F layer, which is about 300 kilometers in altitude. And the white line there is demarcating about 1,500 kilometers, so that you get an idea of the scale. Now, there's wide variety of flows on planetary atmospheres, especially in the ionosphere, since we're talking about magnetic fields, and of course expected on stellar atmosphere as well. If you have a situation like a close binary or very close in exoplanet, then the flow is particularly complex because it involves highly non-equilibrium flows, especially near the terminators, if it's, for example, tightly synchronized. And these flows can not only approach Mach 1, but exceed it by large amounts. So some current simulations are predicting flows that are not only transonic, but maybe going up to Mach 6 or 7. Not necessarily meaning that it's correct, but that those are kind of results they're getting. And the added complexity is, of course, there are huge temperature differences, not only from point to point spatially, but also because of the low density and the speeds, the species can have different temperatures among themselves. So this talk is really about looking at the situation of flows in ionized, rotating stratified, and compressible turbulent flows, and all that in spherical geometry, which hasn't been investigated very much thus far. All right, so typically we start with the fundamental equations. If you're interested in the neutral or unionized atmosphere, you start with this set of equations, the so-called the primitive equation. And basically, this is Navier-Stokes with one sort of simplification, which is this equation. So this is the visa of wind's vertical velocity. This is the Coriolis acceleration, pressure gradients or geopotential gradients. This is the energy equation, compressibility equation. And this thing is hydrostatic balance. So already we're kind of limiting ourselves to large-scale flows. Large scale here meaning that the aspect ratio, that is the lateral extent is much, much greater than the vertical extent. Okay, at least 100 times greater. Now, to this, if you want to start applying this set of equation to study the ionosphere, you will want to add Lorentz force and possibly the induction equation if you're going all the way to MHD situation, and also include ion drag and Joule heating in various F terms in the equations. Okay, so what I'm going to show you now. Oh, it's winding down. It's not going up. It's going down. All right. So what our main approach is to look at this equation, and it's, as you can see, it's already pretty complex. So often what we want to do is either try and solve these equations directly, or try to in some rational, physically plausible way reduce it down and solve the resulting equations, which are still not that trivial to solve. Right? But we're interested in learning the fundamental mechanisms because solving the equations numerically, especially a set as complicated as this one, doesn't always allow you to understand what you're getting out of the simulations. Okay, so here's one way to reduce it down. You essentially you take a vertical average of all the fields, you decompose it into a vertical and the horizontal parts. It's standard technique. And you run through the equations, and what you end up with is essentially a compressible 2.5 dimensional set of equations. Here, 2.5 dimension means it's essentially a sheet of fluid. Here, we're going to envelop the sphere with this sheet of fluid, but this sheet itself is compressible. Okay, so that's where the half dimension comes from. For those of you who are into equations, you might be able to notice that under certain circumstances, the equations reduce down to a very famous set of equations called the shallow water equation, which is often used as a paradigm model to study atmospheric flows. Here, it's a slightly more generalized version of the common or the traditional shallow water equation. Okay, so as I said, if you wanted to study the ionized layer, you add the Lorentz term and then the induction equation. So the set of equation that you ultimately want to solve looks like that. Okay, so I'm going to show you some simulations now that they're not images, but just to give you some simulation parameters, the equations are solved using the pseudospectral algorithm in spherical geometry. So the Legendre basis is used. And even though in the equations here I didn't put down explicit viscosity, there is some viscosity that we put in. It's a type of viscosity called hyperviscosity, which can be fairly easily implemented in a spectral algorithm. And the whole thing is solved in vorticity divergence current charge form. This form of the equation is particularly easy to solve within the spherical algorithm. So, we've done essentially thousands of simulations exploring all the parameter space in full. Some of the calculations are resolution of up to this. There's this T682. This just means there are 682 total and sectoral modes. If you like, it's essentially equivalent to 2,000 by 1,000 longitudinal, latitudinal grid points. However, you shouldn't directly compare that to a standard finite difference method of 2,000 and 1,000 resolution, because of the nature of spectral algorithm. especially its convergence properties, it's although the grid number resolution is the same comparatively, the spectral algorithm is typically, um, I would say, as a rule of thumb, 5 to 6 times more accurate. Okay. And then a word about how we initialize the calculation. We're kind of initializing the flow by randomly stirring the flow at very small scales. We do that in spectral space by randomizing the phase and the amplitude. It's in a state called nonlinearly balanced state, meaning the equations are nonlinear, and if you just haphazardly put down whatever values you want for your field, it's not self-consistent, and typically the calculation blows up. So by balancing the flow, you're almost constraining the flow to not go singular or blow up for finite time. Okay, and then the whole thing is allowed to evolve freely thereafter. Some important quantities to keep in mind: there's energy and potential entropy, magnetic potential cross helicity is conserved in this setup. There's a thing called Froude number, which is essentially like the Mach number of the flow, and the plasma beta, which you already heard about this morning. So I just quickly go on. All right, what you're looking at is, as a control situation, looking at a very simple situation. The sphere is not rotating, purely hydro, and the evolution goes downward here. You're starting with a random small-scale stirring, and you let it freely evolve, and you clearly see a idiosyncratic property of two-dimensional turbulent flow, which is the energy cascades backward, upscale, right, to larger and larger scales. And you can see that from the centroid moving to smaller wave numbers. Never mind about the slopes. We won't talk about the slopes. That's a whole nother talk. Okay. If you allow the compression to be large, for example, as you see on the right, what you're seeing is the plot of potential vorticity. It's the tracer of the flow, a materially conserved quantity in this set of equation. So if you want to know what the fluid is doing, that's the quantity you want to look at. Red means it's rotating clockwise, and blue means it's counterclockwise rotation. And the effect of allowing compressibility to enter into the problem makes the vortices, which start to emerge as a physical manifestation of inverse cascade, looks more blobby. Okay, physically, the reason why that happens is compressibility introduces a length scale in the problem called the deformation radius, which is like the interaction length between vortices. So here, the interaction length is essentially infinite. Here, it's very small, much 2 minutes? Really? It's expensive. Okay. All right. So let me go on more quickly. So the end effect of compressibility is to make the vortices very blobby. Here, this is what happens when you introduce magnetic field. The sphere is still not rotating, and it's essentially acting kind of like a type of compressibility. And that's because there is a b-square term, gradient b-square term in the momentum equation that sits right along with the compressibility term. So it's acting essentially like another type of compressibility. However, if you now rotate the sphere, now you're looking at potential vorticity from top down, from the North Pole, what happens is rotation, because of the Coriolis acceleration, allows a latitudinal restoring force, but not in the east-west zonal direction. So as the vortices merge and they get bigger and bigger, it's constrained to be only of certain size in the latitudinal direction, but it's free to grow essentially as up to the integral scale. And that's what forms these bandit-like structures. So here's the North Pole, here's the equator, and it not only forms these bands, but forms an alternating tight, relax gradient. Now that corresponds to what in geophysical flows called zonal flows. That is eastward mean flow speed as a function of latitude. So you get lots of jets, okay, east-west jets. However, if you turn on the if you turn on the magnetic field, all of a sudden you form no alternating gradient, right? All the jets go away, and the reason is in rotating two-dimensional like turbulence, as you get inverse cascade, the rotation actually stops the cascade at a particular wave number in spectral space that's indicative of the number of these jets from pole to pole. However, the reason that happens is, of course, the 2D turbulence simultaneously conserves energy and entropy. But if you add the magnetic field term, it breaks that symmetry. So you no longer conserve entropy. So even if you inverse cascaded, there's nothing that arrests it. So you can't form the jets. I know I'm out of time, so I just make my last point and then I guess I'll take questions. So this is simply just a series of runs. Everything is exactly the same. The only thing that's changed is amount of initial magnetic field you include. The top is the vorticity, and bottom is the current. That's the curl of the magnetic field. Okay, and you're increasing the magnetic field as you go to the right. Here, there's no current, obviously, because there's no magnetic field. This is pure hydro calculation. If you rotate this sphere, you get lots of banding. It almost looks like Jupiter. Okay, as you introduce the magnetic field, the field acts like the good old frozen-in flow type, and it just simply follows the flow. But there's a sharp transition at this point where the vorticity is starting to look like it's following the current. Okay, it's as if instead of the magnetic field being frozen into the fluid, it's the fluid is frozen into the magnetic field. Okay, in fact, this forms this very tight, almost crystalline-like structure. These vortices do grow over time, but the evolution is very slow, right? And it's absolutely robust. If you even if you perturb it very strongly, it kind of jiggles and then it spits out a couple of vortices, but it still remains very stable. I was going to explain why that happens, but maybe since we only got 2 minutes, I'll just let you look at the summary. So I think, as I pointed out in the introduction, flow in rotating and in spherical geometry, right, which is stratified with magnetic field, quite a lot of physics in it. It's a very complex flow. But we're beginning to see that if you want to study things like hot Jupiters, for example, where the planet is so close to the star, not only is there a strong ionosphere, the ionosphere turns out to be located much deeper in than, say, the Earth is, for obvious reasons. You also saw that magnetic field not only disrupts zonal flows in that situation, there is an abrupt transition depending on what the global mean field strength is. So thank you very much.
All right, one quick question.
I was going to suggest that what you're calling magnetic vortex is what we call as magnetic island.
Yes,
surface.
that's right.
And what may be happening is that you certainly have what you're calling this not sheets. The sheets are really breaking up in your case. And in 2.5 dimensional simulations, that happens in a fairly generic way in MHD flows. But you're quite right that if you have a very strong shear flow in the background, that does change things as opposed to things that are relatively static.
Yeah, so just as a really quick thing, if you look at, this is what we call quasi-geostrophic or really 2D like flow, where the magnetogravity waves are almost completely scaled out of the equation. And you look at the low magnetic field case and high magnetic field case. And it's a very simple problem. You just put down a nested two-patch potential vorticity. That's your vortex. If you perturb the edge, there is a wave that goes along the edge, an edge wave, which is essentially a Rossby wave on a planetary scale. On these jumps, from the reference frame of the vortex, what's happening is there's an edge wave that's going this way, and edge wave going the opposite way. So you have a counter-propagating edge wave, and they're close enough that they actually resonate, and that's what produces the disruption. Now, when you add the magnetic field and you're at small plasma beta situation, the alphane waves are much, much faster compared to the edge wave. So even though you have the counter-propagating waves, they don't resonate, right? It's just too fast to resonate, and that's one reason why it's so stable.
All right, let's thank our speaker again. All right, and for our final talk of the session, we have Dinshal Basara talking about geodesic mesh MHD, a new paradigm for computational astrophysics and space physics applied to spherical systems. Take it away.
Okay, thank you very much, folks. Thank you. We're running late, but I hope I'll get my full 20 minutes. So let's go ahead and talk about this topic, which is GeoMesh MHD, which I would say is kind of a new and happening idea in computational astrophysics, because we have finally understood how to do full MHD with all its niceties on spherical systems in a way which is optimal for spherical systems. So let's have the next transparency. How do I click? Okay, green button. Okay, excellent. This is a full rundown of different systems and what actually causes a problem when you're dealing with astrophysical systems is the fact that you have coordinate singularities. These are purely mathematical singularities at the coordinates, which basically cause two bad things if you're using an r theta phi type of mesh. One is it basically diminishes your time step at the poles of the simulation, and secondly, it actually diminishes your order of accuracy for the simulation. So what we would actually like to do is, instead of working with r theta phi type meshes, go to something which covers the sphere much more uniformly and do simulations in situations like this. So this is a much more isotropic covering of the sphere, and if we can do that, we can actually overcome several important issues. Namely, we can actually do things like global MRI simulations on disks that scale with the radius. We could actually simulate problems where jets interact with pressure gradients in the galactic halo. We could actually do problems in star and planet formation, and already there's a substantial amount of effort underway to actually use these meshes in situations where you're studying the magnetospheres of planets or the heliosphere. And we could also do other interesting, very interesting problems, namely convection in the sun and AGB stars, and perhaps a lot of other issues. Now, why do we actually need to pay careful attention to this issue? It has to do with the fact that turbulence is becoming increasingly important in astrophysics. And if you want to do turbulence, then you actually want to do or satisfy two conflicting requirements. One of which is the fact that you want the turbulence to be minimally dissipated over very long length scales, which basically means that you have to have very high order of accuracy. On the other hand, astrophysical turbulence has high Mach numbers, so you actually want to resolve shocks in the best of ways. And so this actually is meant to catalog the process of doing numerical MHD on a sphere in the best of traditions. So I'll hopefully talk about that. And I've structured this talk so that mostly it's an astrophysics talk. So I'll basically start with a motivating system, namely sub-Keplerian accretion. But I'll first talk about how we've done this simulation in R theta z geometry, the bad kind of geometry. Then I'll basically, with your permission, I will sing the praises of geodesic meshes and their advantages and the challenges of meshing the sphere and how we've overcome those challenges. Then I'll start talking about how we've overcome all the algorithmic issues, so that if you say that a certain algorithm is the best-in-class algorithm for doing a numerical MHD in astrophysics on a structured Cartesian type mesh, then I'll actually show that we replicate all of those traditions within a geodesic mesh, which actually required several years of thinking and hard work. And then I'll talk about numerical results. I'll talk about, then we'll kind of circle back to astrophysics and show that we can actually do certain problems that originally were difficult or not possible to do, but we can now do them on a geodesic mesh in a very nice and comfortable way. And then I'll go ahead and present some conclusions. So let's go ahead and begin. And so one of the things that people who study X-ray systems, X-ray accretion onto X-ray black holes, is sub-Keplerian accretion. In other words, in those problems, the matter rains down on the black hole in a sub-Keplerian fashion, and what happens is that it eventually hits the centrifugal barrier. Where it hits the centrifugal barrier, it shocks, it forms a pressure-driven boundary layer, and that pressure-driven boundary layer is a static structure. It basically forms a funnel, and we would actually like to understand jet formation in such environments. And this problem has been studied hydrodynamically with considerable good effect, and one of the good effects is that people have actually been able to explain the high soft versus low hard transitions that have been observed in these accreting systems. They've also been able to obtain able to partially explain the emergence of quasi-periodic oscillations in such systems. And what we'd actually like to do is explain one more feature, namely jet formation. And as everyone knows, jet formation requires interacting with magnetic fields, so we'd actually like to understand how magnetic fields could drive jetted outflows in such situations. We already know that observations support that. We would also like to understand how the shock could anchor itself in, I'm sorry, the magnetic fields could anchor themselves in the shock and thereby dribble into the accretion disk and therefore sustain extended periods of jet formation. So let's go ahead and do exactly that. And what we have here, I will actually request that this movie be started. So what we have here is RZ geometry, 2.5D simulation, and we have a standing accretion shock shown with the density and velocity overlay. And what you're seeing is episodically, we're going to throw in magnetic field loops. So you're seeing the magnetic field loop come in and become strongly resident at this accretion shock. You saw another one go in. But anytime you have a magnetic field loop coming in, and maybe we can roll this again, you will actually see that you also have the formation of high velocity jets in the funnel. And so we could actually have a very nice complete model of low mass X-ray binaries if we have an ability to actually form jets within the context of this model. So with that understanding, what we'd like to do is demonstrate that with this idea of throwing in loops of magnetic field or episodically throwing in loops of magnetic field, you can actually have a very significant amount of outflow. For example, you could have 10 to 20% of the matter, accreted matter, outflowing in these environments if you have sufficient magnetic activity in these circumstances. So let's go ahead and therefore say that we would like to do these problems in 3 dimensions. And so how would we actually achieve this? This shows you the game plan, where you basically start with an icosahedron and blow the icosahedron outwards so that it runs flush against the surface of a sphere. With that, you basically set up, as it were, 20 great triangles on the surface of the sphere. But notice the beautiful arrangement of this. These 20 great triangles are almost equilateral triangles on the surface of the sphere, which basically means that you naturally get a very high quality mesh on the sphere. And what you do is you essentially go ahead and recursively, adaptively refine this mesh so that with one level of refinement you come here, but if you have multiple levels of refinement, you actually get a mesh like this. And this mesh is actually very nice because it gives you a 2.1 degree resolution of the sphere. And you can actually go ahead and continuously keep refining such a mesh and get even finer resolution of the sphere. Once you have that, you would actually, I'll talk about the third dimension in a minute. It is 3-dimensional. Okay, so what you have now is an ability to actually not be restricted by the time steps at the poles of the mesh, nor be restricted by the order of accuracy at the poles of the mesh. And of course, our intention is to go further onto full GR, where we can actually map or we can actually set up a beautiful mesh as close as possible to the singularity of the event horizon and have the maximum isotropy even in such problems. So what happens is that you essentially extrude the mesh outwards as shown out here. So when you extrude the mesh outwards, each of these mesh elements becomes like a triangular prism, but it's a triangular prism in a radial space, which basically has the technical name of a frustum. And we want to essentially have a perfect good MHD algorithm that works on such frustrums. But let me for 1 second explain why we chose to essentially go with a spherical icosahedron. And that shows that, and you see out here that the mesh is most isotropic for this situation compared to this and this other situation. So with that, let me go ahead and further talk about the algorithm. And the algorithm is essentially based on higher order reconstruction, divergence-free reconstruction of magnetic fields, multidimensional Riemann solvers, and temporal update. Of course, that's a lot of technology. But what you actually achieve effectively is that if you ask the computationalists in this room, they will tell you that the optimal way to do MHD is to actually have face-centered magnetic fields that are updated with edge-centered electric fields so that you have a precise divergence constraint preserving update. And what we've actually achieved is the ability to do the same thing in this context, and that required making many innovations so that we could actually achieve such a thing. So with these innovations, we can actually show that our technology is such that it actually preserves order. So if you have improvements in angular resolution, you can see that our second order scheme preserves second order accuracy, our third order scheme preserves third order accuracy, our fourth order scheme preserves fourth order accuracy. And this is as true for hydrodynamic as for MHD simulations shown here. The chairman asked me to run through the rest of the talk. So we can actually do very stringent test problems, which is a good thing, and we can do shock problems, etc. So we have now a robust code for simulations, and we can actually go ahead and scale up to petascale at least. When exascale comes along, we'll scale up to exascale, I think. And then let's go back to the physics. So here you have a situation where we have a full three-dimensional mesh, very well resolved, and you have subcapillaryan accretion coming onto such a mesh, and I will request that this movie be played. And you can actually see that the simulation is such that it naturally goes ahead and develops a well-resolved accretion shock at this location, along with disk formation out here. So this is verging towards steady state, and if we run it for longer, we can show that it is a good steady state. But it actually shows something else that is interesting out here, where here you've actually seen it in cross-section with the rotation going this way. What I'm going to show you out here is actually what happens in the mid-plane of the situation. And you will actually see, let's go ahead and run this simulation. So you will actually see that you have a very nice disk formation. And furthermore, please observe that you have quasi-periodic oscillations going on in the proto-accretion disk that forms out there. So we actually kill two birds with one stone, namely have full three-dimensional effects and also go ahead and have a nice mechanism for explaining quasi-periodic oscillations in accreting black holes. Now, what about jet formation? The nice thing is that now that we've understood through coarse two-dimensional simulations how to form jets, what we would like to do is have a situation where this currently empty channel is filled in by a jet. And how would we do that? The nice thing is that, or the nice insight is, that you throw in anything approximating a magnetic field. You throw in any magnetic field structure, and the nice thing is that a disk, an accretion disk, physics-wise, always wants to kind of resolve the angular momentum problem. And once you have magnetic fields which allow the most efficient strategy for resolving the angular momentum problem, the accretion disk itself will find for you ways to send matter outwards, thereby reducing angular momentum and solving simultaneously the angular momentum problem and the problem of generating jets for you. And that's exactly what is shown to you out here. So we send in field loops of magnetic field, and this is showing you a time sequence. So initially this funnel-like channel is empty. Then the magnetic field comes here, and you basically start to see that the funnel is getting filled up. Then you go to a later time, and you see that the magnetic activity in the disk has actually caused the funnel to be filled up with an outflow even further, and by now the outflow has reached the boundaries of the mesh. Okay, so this is good timing. So it basically, I'll skip over a couple of transparencies, but this is good timing because it basically tells us that we have found methods to essentially beautifully and nicely isotropically map the sphere and carry out high order, high accuracy simulations that are in the best of astrophysical tradition on such spherical meshes. And we can do so with provably very high order of accuracy, which is extraordinarily important for turbulence problems, but also we can actually ensure that the methods that we've devised are robust in the face of strong shocks, which is needed for high Mach number turbulence. And then we've actually gone ahead and applied it. Okay, now the other nice thing is that we've already achieved petascale, and we have a pathway towards exascale, which is very good. And we can actually now start solving astrophysical problems where we actually show that the shock structure that develops or is intended to develop in subcapillary accretion flows actually does develop, and it's a very stable, persistent shock structure. And we can actually show that by throwing in magnetic field configurations, we can actually explain the launching and outflow of jets. So with that, I will essentially thank you all and look forward to questions. Go ahead.
So one of the more difficult problems in MHD turbulence is making sure that a grid-based code will conserve magnetic helicity properly. Have you tested for that?
Long time ago, Anik Pouquet made me test that within the context of grid-based codes for MHD. And at least up to some point, we were doing well. Now, I'm sure that issue needs to be revisited, perhaps, and we could actually do much more refined tests along those lines. But that paper that we kind of put together has already been published in Physics of Plasmas in 1999. Go ahead.
If you want to have higher and higher resolution, spatial resolution, as you go closer to the center, then it's easy. You can have a logarithmic grid or something like
Yes.
that. But suppose you want
Can you use your microphone, please?
resolution. Scales, then your mesh, you would have to have different degrees of mesh resolution at different radii, and then how do you connect them?
Yes, so what Jerry is saying is essentially, suppose you want to simulate a flared disk like an HH tau, where out here you don't care for the resolution, but in this region you care for higher and higher resolution, and the disk is flared outwards, right? So in that situation, we know how to kind of develop adaptive mesh refinement so that we can adaptively refine in those regions and not have too much resolution at the poles one way or another. So we can do that. Yes. Go ahead.
The equations in log coordinates or whatever.
Yeah, you can solve the equations in log scaled coordinates. No problem.
that would obviate. Then you don't have to use an adaptive grid, for example.
But for the flaring example that I picked, and which probably lay behind Jerry's thinking, you could benefit from it.
Yeah, I mean, you could do both, right?
Yeah. Go ahead.
This is maybe a slightly technical question, but for your higher order reconstruction, your grid is irregular, is the best way to describe it. How do you do the stencil in that case?
There are papers in Journal of Computational Physics that actually we've spearheaded such papers already, which document how this is to be done. And we also have papers now for astrophysical journals documenting the more astrophysics-y sides of things.
But you have to do the reconstruction.
But there is a certain technology and a magic involved. It's not magic, but you have to do very substantial innovation, not like the ones that we do in traditional grid-based Cartesian MHD codes. Yes, so you're right.
All right, let's thank Dinshaw and all our morning speakers again. Over to Mark for the discussion.
Okay, there it is. Okay, can everyone hear me? All right, so I just tried to pull out a couple of themes from this morning's talks. I obviously am not going to cover everything, but these are ones that I hope will at least spark discussion. All right, so I was going to go through these in order, but if reading these, someone is particularly interested in one of them and wants to go out of order, feel free to do so. All right, so the first one, a bunch of talks talked about reconnection and turbulent reconnection and its potential importance in star formation, in other astrophysical contexts, and one thing that makes me nervous is, all right, so in our simulations, we know how reconnection happens. It happens by numerical crap, right? In our simulations, reconnection happens because we're doing simulations that have numerical resistivity, and that's how it happens. All right, so the question is, if we think that turbulent reconnection is an important process, how can we tell if our simulations are getting it right or right enough? All right, so for example, how do we know that we have enough resolution that the answer we're getting isn't dominated by numerical resistivity as opposed to, what should be happening? All right, Blakesley.
One way to do that is, of course, with analytic predictions, right? So different models for reconnection have different scaling laws. So there were a number of papers by like Jegesh Kowal and Alex showing that the predictions for the Lazarian-Vishniak model in terms of scaling up the box size, turning up the turbulence, checking how it depends on resistivity, those scalings seem to match very well with a lot of the predictions of that model. I mean, there's other models as well, but like if you don't have any analytic predictions for any feature of turbulence, it's hard to test if your numerical simulation is getting the physics right or not. I mean, that's even like for the most basic scalings of turbulence, that's how people test whether they've got bugs in their code or whether they're actually getting an inertial range.
All right. Nisha, do you want to comment on that?
May I suggest that there is a different way of looking at this problem or asking the problem, which actually makes a lot of sense, which is to say that now, right now, all the simulation codes just just ask for as much dissipation to be thrown in.
Can you use your seat mic, please?
Oh, can you turn your mic on?
Okay, so okay. So right now, all the numerical codes just ask for as much dissipation to be thrown in as is needed to make the simulation stable and don't care about what you've dissipated away. But there is a different way of looking at the problem through multi-scaling. We're actually, we've done a proposal to kind of propose that to the community. And what you can do out there is actually not put in any numerical dissipation that is just purely numerical, but rather let the problem tell you, based on multi-scaling the problem, how much numerical dissipation you need at each location, and use that numerical dissipation to kind of govern the dissipation. And this is not a bad idea because there are other communities where, for example, understanding hydrodynamical turbulence and having a subscale model for turbulence is sufficiently important in the aerospace community where they in fact do it that way.
Right. Alex?
I would put it in a different way. The prediction of LV99 theory is that there is no flux freezing, essentially, in turbulent fluids. And it has been proven. It has been proven. There is a Nature paper by Ank. It showed numerically that you cannot possibly have the flux freezing in turbulent fluids. And there is no any signatures of tearing instability. The corresponding Lundquist number are too small to have any tearing instability. So we have the turbulent eye connection. It has been proven. On the top of this, we can have additional effects that Amitava was saying. But there were recent work by Hui Li, who with peak code also showed that results that Gregor Shkoval obtained with MHD code on turbulent eye connection stay valid.
Let me try and make the question a little more specific. All right, so I, an idiot who knows nothing about plasma physics, go and run my MHD code. I get some answer for like the magnetic flux in my protostellar cores. All right. I go run it at higher resolution or lower resolution. How do I know I've converged? What do I mean, do I just, continue to be an idiot and run at higher and higher resolution until the answer stops changing? Or do I know I've gotten the turbulent reconnection right when some criterion is satisfied? That's what I'm looking for. Like, how can I, as an idiot, not publish stupid things?
As an idiot, I can there is a particular prediction that connection is in turbulent fluid doesn't depend on microscopic resistivity or anything else. So if you have, and it has been tested.
No, I believe that if it's small enough, but I'm pretty confident that if I ran my simulation at a resolution of 16 cubed, the answer would depend on the numerical resistivity.
Yes, because you will lose turbulence.
So the point is, what's enough?
No, you will not have at 16, you will not have ever.
So I want to know what number is enough. So, okay, Phil, why don't you address that?
So you just need a high enough Lundquist number, maybe around 10 to the 5, which is hard to achieve in three-dimensional simulations, if at all possible.
Okay. Yep. Ethan, and then I think we're going to move on to a different topic.
Okay, so the only thing I would add to that is that because there are lots of things that could potentially be going wrong in your simulation, and you want to know specifically if reconnection is going wrong, then the only thing I can think of is that if at some high resolution, if you put in an artificial resistivity which is larger than what you need to ensure stability of the code, and it doesn't change your answer by itself, then that's not your problem.
Okay. All right. I think we're going to move on to a different topic just because we've spent a third of our time on this one, and I want to get to the others. All right. So, I don't know. Maybe we'll go out of order. I'm interested in this third one. All right. So this was inspired partly by, Dick's talk, but it came up in a lot of other ones too. All right. So we seem to have in local molecular clouds this transition where we go from, we have atomic ISM, which is characterized by being magnetically subcritical and by strong magnetic fields in the sense that, the flows seem to be subalfanic. We've got all these filaments and, all these magnetic structures. All right, and then we go to molecular clouds. And in molecular clouds, the magnetic fields are sort of moderately strong, but we're supercritical, where they'd be transalfanic. Why does chemistry know the first thing about magnetic fields? Right? Like, I can think of no good reason why H2 molecules give a fuck whether the gas is super or subcritical. So why is the transition between these two regimes seemingly associated with the transition, with this chemical transition? And to make the point sharper, suppose I were to go and look at some other galaxy, say M51, where the ISM is mostly molecular, and the H1 that exists is basically just PDRs on the surfaces of molecular clouds that happen to be near B stars where they've gotten dissociated. Will it continue to be true that this sort of magnetic transition is associated with a molecular transition in that galaxy? All right, so I'm interested in hearing thoughts on that.
It's actually my turn to ask a stupid question. Why would it not matter? Don't you have dissipation that differs depending on what the chemistry is?
Not really. The cooling time in all of this gas is basically 0 compared to any mechanical time scale. So it doesn't matter. Yes, the cooling channels change if I have atomic versus molecular, but it doesn't matter because the cooling time is 0. You reach thermal equilibrium instantly.
I thought that in ISM, turbulent dissipation matters a hell of a lot.
Oh, the turbulent dissipation matters, but the rate limiting step has nothing to do with the microphysics of cooling. The rate limiting step is the rate at which you can dissipate the turbulent flow, and then the time it takes to radiate that energy away is basically 0. So, whether my cooling channel is the fine structural lines of carbon plus in the atomic ISM or CO lines in the molecular ISM, doesn't matter. Cooling is instant.
I think it does matter.
You think it does matter? All right.
Yeah, because the cooling, you have a lot
can you
more
push the
cooling
button?
per gram.
Oh, sorry. That one, yeah.
You have a lot more cooling per gram in a molecular region than you do in an atomic region. And so it prevents the temperature from ever getting up above like 20 degrees in a molecular region. Whereas in an atomic region, most of them have temperatures that are much higher than that, and the rate at which the energy can be lost is a lot smaller.
And do you think that is why this sort of transition in magnetic structure is related to the chemical transition?
I think
Well,
it may have something to do with that.
well,
Someone else want to comment on that?
kind of gives you
Didn't show.
your justification for using the isothermal approximation, right?
Well, sure. That's why we frequently approximate molecular clouds as isothermal. But I mean, the CNM, it seems to me, is basically isothermal too. Even the WNM, I would assert, is isothermal in the sense that the radiative timescale is short compared to the mechanical timescale. I don't know, Dick, do you want to comment?
It seems to me that what you're talking about is fundamentally a coincidence. That what really happens at roughly that column density is clouds become self-gravitating. And it also happens to be the column density at which you get the transition from atomic to molecular. There are 2 and maybe 3 cases with the VLA where we measured the Zeeman effect in quite dense H1 gas, and it was supercritical. It was like a molecular cloud, but it was measured in atomic gas.
Okay. So you think it's purely a coincidence, and so if you went to another galaxy, those two just wouldn't coincide anymore?
Well, other than that, the atomic to molecular ratio probably correlates with whether the cloud is self-gravitating or not.
Okay. Blakesley, do you want to?
I completely agree with what Dick said, and the way to test it would be to look at metallicity, right? Because you go to a low metallicity galaxy, and the H1 to H2 transition is different. So if you have like a super awesome telescope that doesn't exist, where you can do Zeeman observations in another galaxy.
Can you do Zeeman splitting in the LMC for us, Dick?
Yeah, but even the LMC and SMC, I don't think have low enough metallicity to.
So you want Zeeman splitting in 1's Wiki 18.
Yeah, exactly. That would be how you test it observationally, and I guess the more practical thing would be to do low metallicity chemistry turbulent simulations, similar to the ones that Philip was showing, where you can populate this N versus B plot and look at how the transition depends on self-gravity versus the H1 to H2 transition, which does strongly depend on the metallicity.
All right. Alex.
I feel that the answers to this second and the third questions can be obtained observation. And we don't need to rely on Zeeman in that case. We can really find out, for example, subalphenic or superalphenic using different techniques, and I now advertise gradient technique for that. The same is applicable to the second issue about phases. Indeed, with polarimetry, it's difficult to trace the transition because of instrumental sensitivity issues. But again, with gradients, we can do this, and we are already doing this.
Okay, well, so fine, we can bring in the second question here, which is somewhat related, which is, to what extent should we think of the transitions between warm ionized, warm neutral, cold neutral, and molecular as places where there are physical discontinuities, all right, where, say, the alphane, so where the structure of the turbulence changes, and to what extent are magnetic field lines and turbulent structures just going across these discontinuities with no physical changes, all right, with no changes in, say, the turbulent structure. So, for example, suppose I had real 3D data, all right, I knew the 3D velocity pattern. would I see a difference in, say, the power spectrum of the turbulence in WNM versus CNM? All right, Jerry.
My question goes back a step. Those three terms, I think, first appeared in the paper of mine, Chris McKee. And I've always wondered how accurate
Use your microphone, please.
accurate they are in describing the actual interstellar medium.
Carl?
And so I would be interested in any comments on this, because we very often have paradigms and mnemonic devices which are very rough, and then people take them seriously, and then the question is, how good are they to actually describe things?
All right. Carl, I believe you have been thrown a softball.
Well, I'd say the WIM and the WNM are certainly different. You can map the WIM with H alpha, and you can map the WNM with H1, and they don't look the same. They're definitely different phases.
You mean they're in different places spatially?
Yeah.
Well, the extremes are real, otherwise the terms wouldn't have been invented. But is there a significant amount of gas that's in between?
There's a lot of gas that is between WNM and CNM. That is in the so-called thermally unstable part. There's a lot of gas there. In the CNM, you made the remark that it's all the same temperature. Well, that's not really quite true. The temperature in the CNM ranges from 16 degrees up to about 500.
So just to clarify, when I say isothermal, in hydrodynamics that has a very different meaning than, so isothermal does not mean it's all at the same temperature when used hydrodynamically. What I mean is that if I write down the energy equation for the gas, all right, so I've got, the fluid terms, and then I've got the heating and cooling terms. What I mean is that the heating and cooling terms are so much larger than the fluid terms, than so the rate of change of the gas energy due to radiative heating or cooling as compared to the rate of change in the gas energy due to, say, adiabatic compression. All right, that the radiative heating and cooling terms are way bigger than any of the fluid terms. And so the temperature is simply dictated by the balance between those two terms, and adiabatic heating or cooling of the gas is an utterly irrelevant process. That's what I mean by isothermal in the fluid dynamics sense. And that's the assumption that we make all the time in numerical simulations. So that's what I mean specifically.
You mean specifically that
adiabatic heating and compression are unimportant. Adiabatic heating of the atomic ISM is not an important process.
Then why does the CNM have such a wide temperature?
Because the radiation field is not uniform, and the density is not uniform.
Come on.
And the density is not uniform. I mean, the temperature can depend on density, but if the temperature just depends on the local density, then that's still isothermal from my standpoint. Dinshar, okay.
Is it the point of your discomfort that you've been using isothermal simulations?
No, no. In fact, I will show some beautiful radiation hydrodynamic simulations in my talk later today. My point, the point I'm trying to make, or the question I'm trying to get at is, right, so to what extent are differences we see in chemistry, which affect how we observe things, reflective of any real physical discontinuity in the fluid, and to what extent are they a chemical discontinuity that has no basis in the physics of the fluid flow, and it's simply a chemical issue?
One point I can make is that we dropped into the isothermal approximation in the 1990s simply because that was the only kind of simulation that we could do. These days, you could actually allow for these radiative heating and cooling terms, and the code would run just fine with no problems. And you
lots
can
of people do.
Back off from the isothermal approximation altogether. That's
and lots of people do. I think that's not the issue. Yes. Oh, can you push your button? Sorry.
I just wanted to urge to go back to Carl's explanation before the discussion of what isothermal really means came up. Because I thought Carl was about to expand on the different his view of this question of are there discontinuities in these different phases? Or maybe
Carl,
I
do you wanna-
misunderstood.
Well, so there are discontinuities between ionized and neutral. That's for sure. WN and CNM and what's in between, the so-called thermally unstable things, are more of a continuum. It's true that CNM histogram of temperature peaks at about 50 or 60 degrees, but there's a wide variation. And it seems to me the reason has to be that the heating and cooling terms cannot keep up with whatever is heating that gas. And a lot of that must be mechanical because we see these big shocks from superbubbles, supershells. That's point number one. Point number two is you're missing a phase. There's something called dark gas. That's
molecular.
Dark gas is an interface, I think probably, is an interface between molecular clouds and atomic clouds. And you were wondering if that interface is sharp. And I think the answer is dark gas probably shows it's not sharp because dark gas is a transition between the two where you can't see it in CO because it's not dense enough to excite it, but you can see it if you look hard enough in other ways.
So do you think the dark gas is magnetically subcritical or supercritical? Or just on the line?
It depends on how big an object you've got.
All right, so Blakesley, I think last comment because we're out of time.
Well, I was just going to get back to the second point here where you mentioned turbulence and how if there's discontinuities in terms of the turbulence, so that can easily be studied and it has been studied. So one example of that is a study by Min-Young Lee, Nick Pingle, and I, where we looked at the Perseus molecular cloud. And Min-Young Lee has beautiful Galfa H1 data where she's looked at the warm neutral medium, cold neutral medium from absorption lines. We also have dust, we have CO, so we have multiple tracers which trace these different phases in and around Perseus. And so we've studied the properties of turbulence there in terms of the velocity power spectrum, the density power spectrum, the PDFs, etc. And we find actually exactly what the multi-phase simulations of a turbulent flow would predict, namely that these different turbulent statistics are continuous, except that when you have phase changes, you also have temperature changes. And so you can easily get yourself into a situation where you go from like a subsonic medium to a supersonic medium based on the temperature change. And those are reflected in the turbulence statistics. So it looks like the turbulence is at least continuous, even though the tracers themselves look like discrete individual tracers.
All right, I know there's more discussion people want to have, but I think people also really want to have lunch. So I think we're gonna cut it off here. Thank you.